Thanks for coming, everyone. Today we're joined by Dr. Fraser Holloway, who's a postdoc in the University of Liverpool within the nuclear instrument, where he works in nuclear instrumentation. So today's going to be talking to us about his research as part of the AGATA collaboration, where he's the lead on the pole shape analysis team. Is that right?
Yeah.
Yep.
Well, pole shape analysis development, but splitting hairs effectively.
Yeah. Okay. Well, when you're ready to get started, please feel free to go ahead.
Yeah. So hi everyone, I'm Fraser. So I'm going to share it off the MacBook, so it might be a little bit laggy. This is my talk. It's on technological advancement with AGATA. So I'll quickly kind of explain the AGATA collaboration, how signal generation kind of works, how we do electronics and event processing. The topic which I'm predominantly kind of going to be focused on during this talk is something called pole shape analysis, which is a technique which we use to infer properties of gamma rays present within high purity germanium crystals, and how we perform that for both single interaction energy depositions and multi-interaction events. How we kind of do some detector characterization and modeling, along with like experimental scanning on detectors, how we perform neutron damage correction, some fabrication, and then some new techniques which we're applying using machine learning in order to improve the performance of our detector systems. So the field of nuclear physics is quite broad. It can be incredibly hyper-focused onto nuclear equations of state. So you start looking at things like deformation. So these are just fairly laggy rotations of prolate spheroids, this pear-shaped nucleus, and I think this is might be a hexadecapole deformation. Various different nuclear kind of models which kind of describe these, and generally we infer their shape, deformation, magnetic quadrupole moments, density, radius, spin and parity from the observation of gamma rays, which correlate from the changes of nuclear state. Nuclear physics also has a huge amount of applications to the real world. So computed imaging is the predominant kind of focus of the instrumentation group here at Liverpool. We also do some kind of fringe work on positron emission tomography and X-ray generation and simulation for medical imaging, and also some work now on like nuclear security and understanding radio protection for like complex security environments. So what I'm predominantly involved in is this development of new instrumentation, and I focus specifically on pole shape analysis. But as you'll kind of hopefully see from this talk, pole shape analysis allows us to infer a lot of new information about these kind of detectors, which we use, hopefully design new detectors, trial new materials, and use new segmentation in order to improve the performance of detector systems and advance fundamental and applied nuclear physics. So gamma rays from nuclei can interact with matter in a variety of different ways. You might know this kind of plot on the top right. This is just showing the effective cross-section of mass attenuation coefficients for the primary interaction methods. So at low energy, you kind of see photoelectric absorption dominating as the dominant interaction method. And these are actually the K and L shells, which kind of cause this these kind of dips here. There's also, in this case, Rayleigh scattering, but you can see it's a few orders of magnitude below photoelectric absorption. Above about 100 keV, you start to see Compton scattering as the predominant effect, which is what I'll predominantly focus on. And then above 1022 keV, you obviously get pair production, which becomes a dominant effect of about 10 MeV. So how these kind of energy depositions manifest in matter, generally, like you will either have, we interact by typically liberating electrons. So in a scintillator detector, you may get light being produced, and in a semiconductor, you generally end up producing a conductive region, which allows us to detect some of charge. So Here's a little bit of physics on constant scattering, which is the kind of the predominant kind of effect which the AGATA detector currently uses. So in AGATA, we try and detect effectively 3 different types of events. So if we're dealing with relativistic beams, we're dealing with gamma rays which have significant Doppler effects. And so being able to localize an energy deposition or a single energy deposition gives us much better Doppler correction. And I'll show you a plot later illustrating this. If we get 2 interactions, we can use the constant scattering formula shown in the bottom left to back project out the Compton cone. And this is quite useful for applied nuclear physics Compton imaging. And if we can get 3 interactions, we can also infer the polarization of the gamma ray, which then allows us to get a better probability distribution for the Compton cone. So, fair amount of maths, a lot of formulas. Ultimately, I don't really care too much about where these gamma rays actually come from. I'm very much focused on determining where the dots are meant to be in high purity germanium. We'll get onto that in a bit. So why high purity germanium? Well, in nuclear physics, it's one of the most powerful materials we can use to measure gamma rays. So it's a very powerful semiconductor for a bunch of reasons. It has a very high density and a very high effective Z, which gives it, which makes it very effective at photoelectric absorption and Compton scattering because these are Z dependent. It's a semiconductor, and so the energy deposition in germanium directly correlates with how much charge that you receive. There's no conversion from like a scintillator detector where you eventually have to go to a photocathode or a voltage multiplier tube. The Fano factor is very high, which means that we get very good resolution when we measure gamma rays. But because the band gap in germanium is so low or very small, we really need cryogenic temperatures in order to cool these to an appropriate level where we can use it for spectroscopy. The other problem is it's actually very expensive to manufacture germanium. So an AGATA crystal, which is about the same size as a coffee mug, this is a little 3D printed version. That's about £250,000. That's not even the most expensive germanium they make. Germanium 76 is about 10 times that. But we'll get onto that a bit later. So this is AGATA, or it was AGATA about 2 years ago when I visited Lignaro. So you can imagine a bunch of these AGATA crystals in kind of a hemispherical configuration. So it gives you about an outer radius of about 50 centimeters. And we do all this nuclear physics within the inner hemisphere. So each AGATA crystal produces about 1 gigabyte of raw data per second. So we're talking, well, actually it's almost 2 now, gigabytes given the higher rates. So we're talking about 0.5 terabyte of data per second raw rate coming from something about the same size as a beach ball. So it's a phenomenal amount of data which AGATA produces. All to just, accelerate the understanding of nuclear structure. So the reason AGATA is quite powerful is it uses this full germanium shell. So typical gamma ray spectrometers will use Compton suppression shield. AGATA doesn't. It uses pole shape analysis in order to really localize signals, and then gamma ray tracking to then track them across multiple crystals. So pole shape analysis is, well, pretty much the kind of linchpin of how AGATA has to work. It's this idea of being able to localize gamma ray interactions by looking at the signals which they produce in the germanium. Fortunately, this is a very computationally extensive and expensive program to use. And so we work on more advanced algorithms that can do this more efficiently. So this is just kind of showing a quick demonstration of what gamma ray tracking does in AGATA. You should be able to see this track in the middle has several energy depositions, and it passes across crystals. But because we can use Compton kinematics, we can come up with a likelihood fit of this gamma ray interacting this way, and we can try and group energy interactions and understand how the energy is deposited in certain locations, back project them, and determine the likelihood and kind of group these into individual gamma rays. So this is just showing a comparison between like an unsegmented traditional kind of arrays. This kind of blue line is the kind of untracked array which you get, and it's dominated by this Doppler broadening. As soon as you start segmenting the detector and adding like crystal centers, you get better resolution, you get better peak prominence, but it's only really when you start adding in pole shape analysis and gamma ray tracking where you start to get the kind of performance which you really need for nuclear structure. The plot below is showing effectively what happens when we use gamma ray tracking to also then aggregate these events, effectively suppressing the competent background or aggregating it into the true peaks. So mildly slideshow looks way better on my laptop, but this is an AGATA crystal. It is segmented into 36 outer electrodes, one core. It's 80 millimeters by 80 millimeters, which is 90 in length. And in AGATA, we have this kind of front segmentation, so it's a 6 by 6. And in order to produce the signals which we use for pole shape analysis, we simulate these in a very bespoke software called ADL3, AGATA Detector Library 3, which takes in properties like the crystal axis orientation, impurity gradient, electric field, it calculates the space charge, which all tells us how charges move through the semiconductor. We then use the weighting potentials, which are basically an application of Fukuyama theorem to effectively convert that charge trajectory into a electrode voltage. And so we record these, we generate a database of signals on a cubic basis of about 50,000 unique positions. Each one of these has a unique signal response. And we basically use this as almost like a lookup table, k nearest neighbor kind of match, where if we get an experimental signal, which I'll show in a bit, we effectively try and figure out the closest match within this database, and that's the position which we use in our PSA. So this is just showing a quick comparison between the kind of experimental signals we get and a calculated one for our basis in the bottom, and we get a very good agreement with some experimental noise, but realistically this is very good. On the left, we kind of see the typical response you get for a core electrode, an outer segment, and this third plot shows something called a transient signal, which is induced by neighboring charges. And all of this gives us the position resolution or the kind of position response in an AGATA crystal, which we need to actually do gamma ray tracking. So we're not the only large volume germanium detector array in existence. Another really good application of pole shape analysis is the Legend experiment. So this is kind of it's like a crossover episode between nuclear physics and particle physics, and it's dedicated to observing neutrino double beta decay of germanium-76. So this is a Q beta beta value of like 2-ish, 2.5, 2 MeV. Which is, of course, when you don't produce a neutrino or an antineutrino, and so you expect the electron to carry all of the energy. So the biggest challenge, which really is present in Legend, is background suppression. There's multiple different sources of background present in Legend, so being able to discriminate between a single site event caused by neutrino double beta decay and multi-site events caused by gamma ray interactions is the predominant source of the background. So currently they use something called an AOV parametric veto, which is heightened by the design of their detectors. So the design of the Legend detectors is an inverted point contact coaxial, and that basically means that interactions in separate parts of the detector have a very different response, and their drift time is very different. So we get multiple interactions or multi-site events, which would only occur from a gamma ray. We can effectively veto these. So at Liverpool, we have detector based on very similar technology to Legend, and this time it's applying some outer segmentation onto the pond contacts. So we have 10 longitudinal segments and 8 azimuthal segments, effectively as a pizza slice on the back of the detector. And this is designed to give us a position-sensitive response in these kind of systems. And this just shows the charge created in a sigma detector in various different positions. You can see the holes travel down to the point contacts, the electrons travel out to the outer electrodes. They all kind of share this kind of charge superhighway path. But because these charge trajectories change and the weighting potentials change, we end up with much more information than what we would get from the Legend detectors. These are also much higher background, so they're not directly applicable for Legend, but they're very interesting to understand how we can make better germanium detectors, how we can understand the effects of crystal axis orientation, charge mobility, how the charge clouds move through germanium, lots of very interesting kind of effects. Coming back to application, Liverpool also designed something with the GRI Plus Compton camera. This is a 3-tier Compton camera using germanium DSSD and a coaxial and a SILI detector. And it's designed for both medical application and nuclear security kind of imaging applications. So this is just a zoomed in view of the germanium DSSD we use. It's a double-sided strip detector. I think it's 11 strips on the AC and the DC side, and you look for charge being registered on the opposing faces in order to localize the interactions. So we have parametric PSA, which uses the charge asymmetry, the transient signals, to try and determine XY position. I mean, you can use rise time and delay analysis to get the depth in the thickness of the detector. So this is there are non-parametric methods. We use a basis k-nearest neighbor optimization, but it only really works within a single interaction site. So in this case, 2 interactions currently is observed as 1, but this is a limitation of that technique. I'll skip this one. So parametric PSA is quite a broad thing. It covers any kind of analysis technique that observes something that can be easily derived. So in this case, this is the T1090 rise time showed for an AGATA crystal. You can kind of see there's some 4-fold kind of mobility kind of happening from the crystal's axis orientation, which kind of goes to 6-fold in this kind of top right due to the segmentation. These techniques are very fast to evaluate, but they have limited performance. And unfortunately, these things, when you try and apply them to multi-interactions, they kind of fall apart. And this is because they would rely on some kind of bijective mapping. And as I'll explain later, multi-interaction PSA is a surjective problem. So non-parametric PSA is a little bit more challenging. It relies on having a very good simulation of your detector, in which you can have a look at the way your detector changes as a function of position, or the interaction position changes. And we can effectively compare a set of simulated signals against our experimental measurement, and we can look for the closest match. So we're effectively doing a k-nearest neighbor search, but we're trying to do this very quickly, but k-nearest neighbor is quite a computationally expensive thing to do. So what do these kind of signals really look like? So in the bottom left, I show a cut through of a coaxial detector, just showing this kind of colorization is meant to indicate the rough kind of radial position. This middle plot shows the kind of pulse profile you get for the hit segment. And you can kind of see how it goes from like effectively like a convex kind of signal into a concave one. And this is due to the anisotropic mobility of electrons in the holes. There's not a huge amount of information here. You can see that when you look at the kind of covariance matrix of these signals, it effectively just forms a singular kind of blob. And this implies that it's effectively just a singular manifold. So if we apply some machine learning methods, particularly UMAP, we can take effectively a high dimensional response, placing each of these signals in about 121 dimensions, and trying to get machine learning effectively to down project it into something that we can start to visualize. So this is just showing how UMAP effectively works under the hood. It effectively forms a graph representation of the data and then down projects it, trying to preserve the strongest connections. And that kind of looks like this. Okay, it doesn't look as bad as I was expecting. Well, there's a singular manifold which is produced, so this data is quite well connected, and the kind of coloring which you see is meant to indicate a kind of radius of the Euclidean representation. And because you kind of have this smooth transition of color, it indicates that actually this is a learnable parameter. Something which is not, well, similarly I kind of show this also for the Z position on the left, where like the main kind of spine of this manifold is a darker blue, indicating a very low Z, showing at the back of the detector and the front of the detector, where you can have these kind of fringy Febvre effects. That's at the front, where there's more signal variation. Not every property can be really inferred using this. So if you apply a degenerate, try and map on a degenerate kind of quantity like the azimuthal position, there's no direct correlation. So this is not something that you can directly learn through machine learning. So in AGATA, because we have 36 outer segments, we get a lot more information than just a standard coaxial detector. So we get, like every coaxial detector, we get a core signal and a hit signal, but you also get a set of these kind of transient signals. And these transient signals give us a lot more information. So when we apply the same UMAP kind of learning technique, the data starts concentrating in a significant number of sub-manifolds, which means that the PSA becomes a lot simpler to kind of learn these kind of properties. So because this data is so well separated, and each kind of sub-manifold has its own distinct structure, we can do a lot more with the PSA, with an AGATA signal. So AGATA's developed a lot of different techniques over the years. This is just kind of showing a plot of the ones that kind of started before my PhD, in which we're never really able to kind of get to this blue region where we have good position resolution with an acceptable kind of computation time. And so I did a whole bunch of work on accelerating the PSA using hierarchical data structures. In this case, this is something called M-tree structure, which builds recursively down in basically hyperspheres of smaller and smaller radius. And this is a space division kind of technique. But there's also greedy techniques such as hierarchical new small world structures, which greedily traverse effectively graphs of higher and higher resolution to try and determine the closest match. So these methods are very much designed to do k nearest neighbor. They kind of actually fail quite spectacularly when you try and give them multiple interactions, and I'll have to explain kind of why in a little bit. But in general, the kind of computational performance we kind of saw with these kind of methods kind of outstripped the kind of conventional methods we were using. So this is just kind of showing the performance in the kind of AGATA crystal. So on the right, you kind of see it's got a propensity to predict away from segmentation boundaries. But in general, the performance here is quite good. And it scales roughly linear with the amount of noise applied. This is for synthetic data. Looking at the kind of rates which we get for this, this pink one on the bottom is a standard convolutional neural network. And then basically the kind of takeaway from this was that the GPU accelerated approximate nearest neighbor technique face was the technique which was recommended for collaboration to implement for RPSA. Taking some experimental data at Liverpool, we used a cesium-137 source, about 1 gigabecquerel, collimated into a 1 millimeter beam, shot directly up at an AGATA crystal, Compton scattered 90 degrees, and then detected in coincidence through secondary collimation into a BGO array. This is a kinematically quite a rare kind of thing to happen. So we're fairly limited in the statistics, but we're able to kind of probe how these methods apply to a reasonable space and kind of volume. In general, this was within the tolerance for what we need for the AGATA collaboration. So we're also pretty happy with this. And then this is just a quick summary of the different methods that we tried. And you can see this GPU accelerated algorithm was the one which was arguably the fastest, running at almost a megahertz or half a megahertz with a pretty high effective recall. So within AGATA, we often have multiple interactions happening within the crystal. In this case, one interaction happening at the front and one happening at the back. And we can window these kind of things and give them to our algorithms to process them. Unfortunately, a lot of the time, what we end up getting is two interactions which happen to be in the same segment. And there is no way to directly separate these events. They're very high covariance within the same segment. There's no specific windowing we can apply in the time domain. And so this is effectively just a combined signal. And this has quite a big ramifications for the kind of the tracking, because kinematically the response from the PSA doesn't actually make sense. So this happens in about 30% of cases, and we can validate this with a GN4 simulation plugged into our simulation. Yeah, so this is a significant problem. That's what my postdoc has largely been based on trying to solve. And it effectively causes clustering within the detector, effectively weighting towards the barycenter of the segment centers. And so in order to kind of understand this, you kind of need to understand why these things kind of exist. So for multiple interaction kind of solutions, the solution space is very complex. So single interaction PSA is effectively solving the localization of Voronoi cells. So you kind of have these quite nice dips in the kind of chi-squared space, where if you're in a reasonably close to your basis points, you'll likely find the correct answer. When you try and apply this to multiple interactions, you end up with these large troughs in your optimization space, and there's no distinct gradient, which you can optimize off. It also these kind of domains scale of n squared, so you end up with, if you imagine there's about 1,000 basis points in each segment, you now have about 1 million polytopes domains for your two interaction PSA. So this becomes a very hard thing for machine learning to solve, because your solution space is so fractured. It's not a nice smooth kind of transition which you get with one interaction. So there are a few different machine learning methods which can handle this. So composite networks is the first one. So you might know this as dual-headed networks, in which you can divide the regression of the position, the energy fraction, and place them into dedicated networks. These can be quite challenging to train, again, because of this solution space. You can try and form a derivative of the chi-squared minimizations, Reta collaboration use, which is pretty straightforward. There's singular value deconvolution and non-negative matrix factorization, which we've tried to use, but there were limitations on that due to how many interactions it predicts. And there's also sparse coding or sparse approximation. So we can use L1 lasso regression, which is quite a common technique used in machine learning, or we can use orthogonal matching pursuit, which is another quite promising method. So the problem largely with trying to use this with machine learning is that we are still trying to link this back to the physics. So in this case, we really want this WK, or the sums of all the WK, to equal 1. And if we don't get that, then we are adding more energy into our PSA algorithm than what we're really expecting. So a different method is to use a more analytical approach. So this is a technique known as simplicial demixing, and which you can describe multi-interaction events as a projection of a simplex. So this is just solving a really large amount of combinatorics of linear algebra. In this case, we're just trying to infer this position S that's orthogonal to our query point that's somehow made from points C1 and C2. And we do that effectively by looking at the L2 square of these kind of distances and doing a deconvolution of that to find the correct match. And so this applies very well for two interactions. It applies very well for three interactions. The math works relatively well for up to 9 interactions. You start getting issues with what's the word, like float precision. So you have to start moving to long longs, which can be a problem. But the real problem within this is the actual combinatorics of trying to solve this. So we're talking 1 million combinations to look through for two interactions is relatively fine. 500 million for three interactions starts to be a problem, which you then need to offload onto a GPU. If you're trying to solve 9 interactions, which we can have within AGATA, this outpaces what we can reasonably do computationally. Now we can kind of split this and solve the problem using this kind of windowing technique because the metric is commutative. So you don't necessarily have to solve all 9 interactions at the same time. You can kind of solve locally free at time and then basically rejig the answer once you have a better fit. And we're kind of investigating this as kind of like a global fitter. But this work is a lot of maths. So I think I'd have to kind of show you how to do a Cayley-Menger determinant. But I put it on one slide and I think it was about 100 terms for the free interaction. It gets a bit complex. But in all, the algorithm works very well to kind of form these fits. So this is 9 interactions within AGATA. It's a completely covariant thing. All of these signals are very much overlapping, but it does a very good job at fitting to the simulated data. Just kind of showing you some quick comparisons between this kind of simplicial deconvolution, this orthogonal matching pursuit, L1 lasso regression, and a two-headed network, so these kind of composite networks. This plot on the right, effectively you want this line to be, the deviation to be as low as possible, with slowly increasing the amount of noise. And so the green line, this kind of simplicial deconvolution being at the bottom is very good. You can see that they all kind of really approach the same kind of trend. But there's also like there's a lower limit on the performance of OMP, lasso, and the two-headed network, where they never really get within the actual predicted value for a noiseless signal. Similarly, this is showing the fit effectively compared against the underlying signal. So this is effectively, rather than comparing what the PSA is predicting against the noisy signal, we look at what the noiseless one's doing. And it's a similar kind of thing. Effectively, there is a limit on how much or how well the machine learning methods can approximate the signals. But the simplicial one, because it has effectively a direct knowledge of the underlying signal convolutions, and it kind of look through an exhaustive list, it's able to find a pretty good match that's still perturbed by noise. We start looking at like how well it can predict the actual positions. So in this case, we want the points to be as high as possible, close to 1. You can see they all drop off as you increase the amount of noise, but the lasso and the OMP algorithms really struggle to actually identify the correct index. They actually start to kind of cluster within effectively solutions which they found, which are like, it's hard to explain, but there's some solutions which they prefer over actually like the proper fit. So in general, the simplicial algorithm kind of does this deconvolution the best, but unfortunately it's incredibly slow. So rather than looking through possibly millions or billions of combinations, we needed a better way to be able to quickly infer which solutions we need to look at. And so the approach which I took was to start using something called hypertrees or hypergraphs. And these are a hierarchical data structure which effectively takes graph structures, kind of creates like projections of two graph structures which are orthogonal, and then looks at the connections between them. So in this case, on the right, we're seeing something called a hyperemetry, which is effectively a way which you can approximate the kind of combinations. So effectively what this algorithm does, we have this query point Q. We try and see if it's covered by the radii of the mother points, so P1, P2. If it's able to be covered by an interpolation of that, it's then passed on as a valid kind of signal. You can see that there's no way to create any kind of covering from P2 to P3 or P1 to P3. So it means that realistically, we only have to look at the combinations of the daughters of these points. So this approach then gets applied recursively. Depending on the complexity of the signal, you might have this run over maybe 5 or 6 different layers, but this algorithm effectively self-organizes and aggregates. The second approach is to apply effectively a greedy traversal, where you have 2 nodes which are able to move, but we found this doesn't really work because it gets stuck in local minima. A secondary approach is to try and use machine learning to try and produce these structures. So self-organizing maps or Cahonan organizing maps are a graph neural net originally designed to kind of understand trends within data. So they effectively, it's a competitive learning method in which you basically have a set of weight matrices which then try and organize onto a data onto some underlying data. And then they're able to percolate how their updated vector kind of crosses around the graph until the map actually solidifies. Kind of a bit hard to explain. This is a little animation kind of showing it. There's an underlying sigmoid function here, and the self-organizing map is effectively able to kind of learn this. And then for each iteration, it starts very large and then it moves to sharper, but smaller domain kind of changes. So this is a cardinality 1 SOM, which effectively learns cardinality 1 data. Applying this onto kind of data, which is almost more like kind of 2D, or this is still high dimensional. You can apply this onto kind of a mesh. And then if you kind of remove this, or like apply this onto a hierarchical structure, you can get some good graph SOM, which is effectively a way in which you can pass these updated vectors up and down the graph. And so this is able to learn a hierarchical representation of the data with different approximations at different levels. And so this is then a directly navigatable structure, which the simplicial algorithms can use. So once we have this kind of self-organizing map, it then gets converted into a polylinear simplex. And so this plot on the right is actually showing you the domains of an approximation of this coaxial detector. And effectively, we can do this simplicial kind of approximation on the map to figure out a better or a very quick approximation of an underlying value. What's quite nice about this is it also can be used to then infer the number of interactions present within the signal. So if you have a single interaction, you expect it to exist somewhere within the signal manifold. If you have 2 interactions, it won't exist anywhere within the manifold. You'll get a large distance from the best point that this algorithm can give you. But you'll get a low distance if you use the prior, assuming that it's made of an interpolation. So for legend, I guess it's true for the TSSD. So this is working for a single interaction. Effectively, we just did a very similar thing to the AGATA crystal, where we had a look at the depth of interaction. It's able to predict the depth quite well, and this is able to run about 1.5 megahertz in comparison to about 6 kilohertz. Very similar performance, but it produces kind of a continuous function rather than k nearest neighbor, which is discretized. On AGATA, using the same data from before, we apply this technique, and again, it does not perform as well as the k nearest neighbor method, but it's several orders well, it's 2 orders of magnitude faster than the k nearest neighbor, which makes it quite appropriate to kind of use as almost like a pre-filter, where we can actually identify the number of interactions before we give it to the full PSA. I think finally for the legend experiment, this is very useful for like a multi-interaction veto. And this is what I was trying to explain earlier, where if you have a single interaction, the prediction from the multi-interaction PSA and the single interaction PSA will largely overlap because they'll get very similar answers. If your event is comprised of two interactions, you get a very big discrepancy between the two. Your single interaction deviation will be very high, your double interaction deviation will be very low. So we find a much better fit for two interactions. We get an inference of where these interactions were and also what their energy fraction is, which is very useful if we can get digitized signals. So now I'm moving just onto some other kind of machine learning used within the AGATA collaboration. So this is some work on effectively a convolutional neural network used to predict kind of scan data. So we're trying to use PSA in quite an interesting way. So effectively we scan an AGATA crystal vertically, which gives us our X and our Y position. We get a neural network to try and predict X, Y, and Z, but we don't penalize the Z prediction. We then rotate our crystal 90 degrees, in which we, again, try and predict X, Y, and Z, but we don't penalize the Y. And so the training procedure flip-flops between these two, and our loss function penalizes the data which is kind of trained off. But effectively, you learn proper X, Y, and Z position from alternating data where you only really have two of the three at any one time. We're also developing this technique for to do self-calibration using Compton kinematics. So this is coming from a group in New York, in which we use the position sensitivity of AGATA to self-calibrate the detector system. So this is based on this idea of kind of hit collections. It's quite a complex kind of technique, but effectively it tries to iteratively explain the physics by like subdividing data. So we start with like a kind of prior weighting these kind of hit collections at the center of the segments. So you can see there's this kind of star kind of pattern coming from the six-fold segmentation. After, I think, a set number of iterations, it starts to kind of eventually coalesce into our actual AGATA crystal. And there's still some issues present because of charge sharing and kind of fold determination. This technique is very useful in producing like an experimentally derived basis we can use for PSA. I think this is the last technique I'm going to talk about, which is kind of graph neural networks for gamma ray tracking. So gamma ray tracking is generally based off this kind of Compton sequencing and minimization of either the energy or the angles of gamma rays. We're just trying to aggregate energy depositions and their positions. But we can also feed this into a neural network, or specifically a graph neural network, where we have a fully connected graph network, and then we evaluate this using tens of billions of GN4 simulated data to try and properly aggregate and explain this data system. So, I mean, we've got very good performance with this, but right now it's very much on a toy model. So this is effectively just a germanium shell. There's no segmentation, there's no additional effects. So this still needs a lot of work. So I think that's all I've got, but thank you for listening. If you have any questions.
So if anyone's got any questions online, I think because we're on Teams now, you have to raise your hand, and then I can, I think, make you a presenter, and then you can ask a question. So anyone online just with questions, just raise your hand. Otherwise, we'll go to the room first.
So you talked a lot about that this is very difficult. You need to use very sophisticated techniques to get the positions out. What would be the most important thing to improve about the readout of these detectors so that you gave it an easier problem to solve?
Okay, that's a very interesting question. Okay, so right now the segmentation in AGATA, you can see it's this kind of 6x6 segmentation. That design was finalized, I think, about 20 years ago through an agreement with Miriam, the company which will make these detectors. and optimized in order to try and get one interaction happening per segment. And we kind of expected to try and use parametric methods in order to localize interactions. What we're now seeing largely is really what is the best kind of segmentation we can actually apply to the outside of the detector to make better signals to then reduce, well, make high dimensional response more complex, so the PSA has more information to work off. Right now, it's an open question. I think the answer is likely we simulate our detector at the highest resolution we can, and then we have a machine learning algorithm which tries to preserve the topology while reducing the segmentation. We have a 3-axis CNC arm which can do photolithography of high purity germanium crystals, but we don't know what the segmentation should be. So there's ideally we move to a better segmentation, which gives us more information, increases the cardinality of signals, which then reduces the degenerate signals which we see. But there's additional electronic effects and challenges in actually making these things, because obviously we have to get a company to build these, and if there's a high enough failure rate, they won't. So the design of new detectors informed by the signal response and what the PSA can achievably do is the kind of next logical step in pushing the performance of these systems.
Is there anything you can do with better readout electronics? So sort of more sensitive, better timing?
So you can, well, I guess if you reduce the noise, you reduce the jitter in the high dimensional space, but it doesn't necessarily affect how the k-nearest neighbor is doing because it's jittering around in the space, but still in a potential well effectively. So reducing the noise is something that we work on quite well. If you increase the sampling rate, you effectively move to a higher resolution, but it doesn't influence the actual underlying shape of the response either. So we work largely on trying to reduce the influence of the preamplifier on the shaping of the signals. The noise is, well, the lowest we can get within nuclear physics. We have like charge reset for the preamplifiers, which is very good, and we can output data at a very high throughput, but there are limitations on what we can do electronically. I mean, the other option is we move to a cryogenic ASIC in order to do this very much at the lower noise level, but that's a very significant challenge. We have people working on, but it's still very much in like a very early TRL.
We've got a question online from one Aravinda Pereira. So if I make him presenter, hopefully he can ask the question. Okay, Aravinda, you should be able to unmute yourself now.
Lou, thanks for the talk. That was great. I was wondering, is there a way to kind of use the machinery you have to do maybe like semi-rigorous uncertainty quantification on the reconstruction? Is there a way to like assign an error bar to what you think your pulse corresponds to?
Like a bootstrapping technique. Yeah, there's a couple options.
Yeah.
So, I mean, the assessment of how the PSA is doing is quite tricky because you can evaluate the Doppler broadening, which is the easiest kind of way, but that gives you X and Y, and there's the kind of Z dependence is kind of gone, or it kind of affects the X and Y because it's a projection. We have, I guess we could use inverse Compton kinematics. So we could put into like the gamma beam they have at Cockcroft, one way to do it. There are some ways, it's just tricky. Obviously you can start just applying noise onto your data. That really doesn't tell you much about the underlying signal quality. It's just the sensitivity of, I guess, your algorithm, which I guess is kind of what you want. There are options. It's just the problem is that you can do a very wonderful measurement of the kind of the noise of our test cryostats. It's very different to as soon as we put them into the array where we have these things at very different angles when they're capacitively coupled. There's a lot of quite challenging effects that we can't replicate in clean environments. So that's kind of why we're doing this stuff with these self-calibrating kind of detect, this technique here, where we can try and fold in the effects of stuff like neutron damage or electronics, really produce a realistic actual basis which we can use in our PSA.
Cool, thanks. Is there a way to do it for just for the algorithmic uncertainty as opposed to experimental? So I'm guessing the answer you get is not a definite unique solution.
Yeah, it shouldn't be. I guess you could have a look at. Yeah, you have to somehow estimate the size of the domains, which is tricky in the high-dimensional space. I mean, they're not particularly nice things. They're not great polytopes to work on. You could increase the amount of noise until we get a misclassification and have a look at how the energy changes. So I guess it's something which we're looking into, but it's still meant to be folded back into the physics. So I mean, if I tell you like the uncertainty in the energy prediction for the PSA doesn't have any real physical representation, so it's actually folded into the gamma ray tracking, in which you would then look at the spectral response.
Okay, cool. Thank you.
Thanks, Aravinda. Any questions in the room? If not, I guess one last one for me. Is the purity of the germanium crystals something that changes with time? Can you just assume that they're always to the manufacturer specifications?
Interesting question. Okay, so when you undergo like a nuclear physics experiment, you get spallation products, you get significant neutron damage, you get neutron activation of the germanium, and you get crystal defects. So your impurity gradient does change significantly. We can anneal the detectors, which reduces some of these effects, but that's typically done to remove the crystal imperfections. It kind of resets the lattice. A lot of these crystals are 10, 15 years old, which can really, we don't necessarily know how well they correlate to what the manufacturer gave us in the first place. But they're not going to get better, they definitely got worse.
So with respect to your reconstructions then, is this like a pretty low order effect that's not something you need to worry about? Or can it be?
It's something I'm letting other people worry about. We have issues present within lithium possibly drifting from the core contact. We have, crystal dislocations. There's a bunch of very nice effects which may be affecting how this PSA works. But realistically, we're the only collaboration which could possibly see in the first place. So no one tries to do anything as advanced as this. So if we tackle it, then we're going to be the only people that actually benefit from it.
Right. Could you speak about the collaboration as a whole? So you've got these, large number of scientists, different universities. You've also got the company you work with, Varian. The fact that it's all kind of very expensive to kind of produce. What's the the corporate and academic interest in this, and how does the economics of it work?
I think AGATA is a really great launching platform for any kind of data analysis when it comes to nuclear physics. We get to really play around with really understanding what you can get from germanium. There's lots of investigative studies which we've done on segmentation, charge mobility, all this kind of PSA work, which is only really possible with AGATA. It's the only collaboration that's got enough money and enough actual data and support to be able to really produce tangible results. It's still used as a forefront gamma ray spectrometer in Europe, but it's also very much a research grade kind of system in order for us to try new instrumentation techniques. Now with Miriam, they see these kind of systems as not directly commercially viable. You can buy an AGATA crystal if you really want. No one's going to buy an AGATA crystal for anything commercially useful in the near future. But the kind of techniques which we use to develop these large volumes, how we develop new segmentation, most likely lead to new interesting commercial grade detectors, which we may use for content imaging, may use for improving energy resolution and timing resolution, all things which are very useful for, let's say, nuclear security, medical imaging, radioisotope identification, lots of very interesting uses. And their development is only possible because we really demand the kind of best kind of instrumentation you can do in nuclear physics.
Cool. All right. Well, thanks very much.